Hello everyone. So welcome to another new playlist on the topic of Thevenin's theorem applied to DC networks. Although I may consider AC networks also later, but as of now, for the time being, I'll be doing some problems using DC networks for demonstrating the working of Thevenin's theorem. So if you see this question and if you are familiar with my channel, you may be familiar with this question also. So in another playlist, if I go back in this, I had solved the same exact problem using superposition theorem, and the problem is same. Find the current in 1 ohm resistance, and we found the current. So finally, it looks like the current that we found was 2.06 amperes, and there was a particular procedure that we followed to apply the superposition theorem. Now coming to this video, now we are using a different procedure and applying Thevenin's theorem to solve this particular problem. Okay, so let's see, because the circuit is same, the answers of irrespective of the theorem that we applied for solving, the answers of physically what will be the current in this 1 ohm resistance should match for both the procedures. If the answers are not matching, somewhere I have made a mistake either here or in my earlier video. So let us see how it goes. Okay. So you and those who are aware of Thevenin's theorem, you can pause this video and try to solve it yourself and compare your answers with my answers. So otherwise follow along with me and I will be explaining how to use Thevenin's theorem to solve this particular circuit. Okay. So what the Thevenin's theorem says is you need a single load resistance. Okay, so that means the resistance in which we are interested to find the current. Okay, so in this case it is 1 ohm resistance. So you put a couple of points, as identifying the nodes. Okay, so let's call this A and B. Okay, so this A and B are the two nodes across which we are now interested to find the this 1 ohm resistance where we are interested. So basically this is our RL, load resistance. Okay. So now what is the step? So Thevenin's theorem. So step 1 is find Thevenin's impedance RTH or Thevenin's resistance. So how to find Thevenin's resistance? Remove the load resistance, short circuit the voltage sources and open circuit the current sources if any, and then find the resistance between the 2 points. So if I redraw the circuit, first I remove the load resistance, then I have this point A, then I have like this and B. So this is 0.05 ohms and this is 0.04 ohms. Okay, so this becomes the circuit because I have to remove the load resistance, I have to short circuit the voltage sources. So the voltage sources are short circuited or voltage sources are replaced with their internal voltages, whatever. So now we got this one. Now what is the resistance between AB? So nothing but Thevenin's resistance, which is nothing but 0.05 parallel with 0.04. Okay. So parallel combination of two resistances is R1 multiplied by R2 divided by R1 plus R2. Okay. So what is R1 plus R2 in this case? 0.09. Okay. So 0.05 multiplied by 0.04 divided by 0.09. Okay. So I'm getting 0.0222. Okay. So 0.0222 ohms. Okay. So like this I'm getting the Thevenin's resistance. That step 1 is completed in the Thevenin's theorem. Now come to step 2. So find Thevenin's voltage VTH. What is the Thevenin's voltage is? Introduce all the sources back into the circuit, but still the load resistance is removed, and find the voltage drop between VAB. Okay, so let's see. Let me explain that. So if I introduce the voltage sources, so I'll get something like this. So in this case, what is the VAB is the question we are asking. So 0.05, 0.04, this is 2.05 and this is 2.15. Now, if I introduce these two sources back, what will be the current I have to find out? Based on that, I can apply the Kirchhoff's voltage law to find VAB. Now what will be the current? You notice that these two battery voltage sources are opposing each other, because see, now there is no current in this part and no current in this part, so only a single loop is there, and these two voltage sources, negative is connected to negative, positive is connected to positive, they are opposing each other. So therefore the net resultant voltage will be whichever is higher. So 2.15 is more than 2.05, so the net voltage will be the difference of these two, and then the current will be the whatever is the net voltage divided by the total. These two will be in series now. 0.04 and 0.05 will become series circuit. Okay, so the current will be simply 2.15 minus 2.05 divided by 0.05 plus 0.04. Okay, so the total voltage divided by total resistance. So that will be the current in the loop. Okay, so let's do that. 2.15 minus 2.05, so that is 0.1 volts divided by 0.09. Okay, so that is the total, this one, and then 1.1111 amperes. Okay, so here I will get current as 1.111 amperes. Now what is the direction of the current? The direction of the current will be like this. Okay, so the arrow points here rightwards, 1.1111, and the same current will go upwards here and it will go backwards like this. Okay, so 1.11111 backwards like this. Okay. Now how to find VAB? Okay, so Thevenin's voltage is nothing but V of A with respect to B. Okay, so what is V of A with respect to B? Apply Kirchhoff's voltage law from B to A. So how do I apply Kirchhoff's voltage law from B to A? I start at B, so from this point I move backward. Now I am going against the current, that means my potential is increasing. Okay, so I go to higher potential, right? Because I am going against the current goes from high voltage to low voltage. So whereas my application of Kirchhoff's voltage law is from B to A, so from here to here if I go, what happens? It will be increasing my potential. So VAB equal to plus 0.04 multiplied by 1.11111. Okay, then I am at this point. Now from positive terminal I am going towards negative terminal. I step down my voltage by 2.15 volts, so minus 2.15. so this will be the resultant voltage VAB. Okay, so let us do that. 0.04 multiplied by 1.11111, I got something minus 2.15. Okay, so I am getting a negative voltage 2.1055. Okay, so minus 2.1055 volts. What does this mean? VAB, so potential of A with respect to B is actually lower potential. Okay, anyway, so we got the VTH. Okay, so VTH equal to, now step 3 is we draw the Thevenin's equivalent, Thevenin's circuit. So how to draw the Thevenin's circuit? So we have these points A and B, and here we have a like this. Okay, so this is called RTH, Thevenin's impedance, Thevenin's resistance, and VTH is Thevenin's voltage. See, why I given negative up and positive down is because we got this value like this. The A is supposed to be on the negative side and B is supposed to be on the positive side. Okay, so minus 2.1055 volt, and what is the RTH? I calculated here 0.220222, 0.02222. So this is my Thevenin source. Now to this source, Thevenin source, I am reconnecting back my load resistance, that is 3 ohms. Okay, so my 3 ohm load resistance I am connecting. So now what is the simple formula for current in this? So simply voltage divided by the current. Okay, so load current IL is nothing but Thevenin's voltage divided by Thevenin's resistance plus load resistance. Okay, this is simple formula. So that will be minus 2.1055 divided by 0.02222 so on plus 3. Okay. So what is my current now? So minus 2.1055 divided by 0.022222. I'm sorry, minus 2.1055 divided by 3.022222. Okay, so I am getting minus 0.69667 amperes. Okay, so this is my current in the 3 ohms resistance. Okay, what does this minus sign indicate? So minus sign indicate that, see, in this case the current is like this, right? But actually the current will be coming out of B and going into the A, so it is the reverse. So that's it. So but then the magnitude is 0.69667. So now I don't remember, but let's verify, go back and verify whether our solution matches with the this one. Okay. Okay, I think here there is a problem. The answer is not matching. So let me just pause the video and then find out where I made the mistake. Okay, I'm sorry, I figured out where the mistake was. So the mistake was here at this point where the resistance is not 1 ohm. It is actually not 3 ohms. It is actually 1 ohm. Okay, so here the load resistance is 1 ohm. Okay, so not 3 ohms. Sorry. So load resistance here is 1 ohm. Okay. So I got confused with our earlier problem or another problem where the load resistance was 3 ohms. Okay. Anyway, that was a mistake. So now what will be the load current? So the load current will be minus 2.1055 divided by 1.022222, so on. Okay. So now I am getting the total current minus 2.0597, or I can say minus 2.06 amperes. Okay, so this is the current in the 1 ohm resistance. Now this is a current going from A to B. Okay, so that is why it is minus sign. Or current from B to A, IBA. Okay, so is plus 2.06 amperes. Okay, so now if I go back to my superposition theorem, this problem, so exactly the answer was 2.0597. Okay, so exactly I also got 2.0597. I rounded off to 2.06. Here also I rounded off to 2.06. Okay, so this proves that your superposition theorem or you apply Thevenin's theorem, your final result will be exactly matching. As long as you don't do mistakes like what I did and you apply this theorem accurately, you will get the correct result. So this is the first video. So again, if you go back to my playlist on my channel on superposition theorem, see, one problem I solved on this one, second problem I solved for this circuit, and third problem I solved for this circuit, fourth problem I solved for this circuit. Like that, I have actually solved 7 problems using superposition theorem. Now my idea is to solve all these problems. In fact, we cannot solve all the problems. Some of the problems are not suitable or applicable in the case of Thevenin's theorem. See, for example, if you see this question, here we are saying find I1, I2, I3. 3 different currents we are asking. What is I1, what is I2, I. But the Thevenin's theorem will be only for calculating current in one load resistance. So finally, whatever is the 3 ohm resistance or 1 ohm resistance, whatever you identify load resistance. So this problem we may not be able to, we can still solve it, but we have to do more steps, individually we have to apply Thevenin's theorem multiple times, but that is not required. So we will not do this problem, but whatever problems are applicable, we will be solving. Okay, so welcome to this new playlist on Thevenin's theorem. I'm sorry. So this is the problem that we just solved. Welcome to this new problem on playlist on Thevenin's theorem. This is the first video, and I'll be making more videos in the subsequent videos on the playlist. Thank you so much. See you in the next video.